Alright, I think we're recording. Had some issues this morning, but should get this up soon. This lecture is going to be about probability. Now, first, let's kind of situate this talk on probability within the other things we've been doing in the class. So, we talked a lot about descriptive statistics, including talking about z-scores, which are a descriptive technique, the way we've talked about them so far. Now what we can do is we can combine the concept of z-scores with hypothesis testing, which is a chapter that's coming up soon, in order to create a type of test that we might refer to as the z-test. That's how the book refers to it. We can also combine with hypothesis testing in order to create an inferential technique called the t-test that is based on the z-test. But that's getting ahead of ourselves, because before we can talk about the t-test, before we can understand what's going on in the t-test, we need to understand the distribution of sample means. So, just to kind of situate us in the class, where we want to go from here is we want to start inferential statistics. But before we can start talking about inferential statistics, we need to understand the distribution of sampling means. We also need to understand the basics of hypothesis testing. And in order to understand the distribution of sample means and to really understand how hypothesis testing works, we're going to have to review probability. So that's why probability comes first. Next, we're going to talk about the distribution of sample means and hypothesis testing. And then finally, we're going to get to the t-test. So if you're looking ahead and reading ahead in the book, know that t-tests are coming up, and that's going to be very important. But we got to get through some other stuff first. So let's get started talking about probability. What does probability have to do with inferential statistics? Because that's what we're preparing for. We can never deal in certainty in inferential statistics because of sampling error. We've been talking about sampling error earlier in the class. So instead of dealing in certainty, we want to deal instead in probability. Likelihood is the one-word definition for probability. And in this class, we'll also be using probability and proportion almost the exact same way. So dealing with probability, we're trying to predict the possibility of an event's occurrence. So let's say that we have two bags of marbles. One is 50-50 black and white. The other is 10 black, 90 white. So one has 50 black, 50 white. Number two has 10 black, 90 white. If I draw 4 marbles in a row and they are all white, which bag is it more likely that they came from? So in this case, it's more likely they came from the bag that had 90 white marbles. Although we're not 100% sure that that's the case. Probability is a method for measuring and quantifying the likelihood of obtaining a specific sample from a specific population in terms of inferential statistics. So probability, the mathematical definition would be a fraction or a proportion, or as we said, the likelihood. Probability of a specific outcome is determined by a ratio comparing the frequency of an occurrence for that outcome to the total number of possible outcomes. You can think of it in terms, that definition gets jumbled up. Think of it in terms of a coin flip. What is the probability of obtaining a coin flip? Let's say a result of heads. If you flip a coin, there is one side of the coin that is heads divided by 2 possible sides to the coin. 1 divided by 2 is 0.5 or 50%. There's a 50% likelihood of obtaining heads if you flip one coin. Looking at the equation for this, the probability of an event is equal to the number of ways the event can happen divided by the number of possible events. So if we flip a coin, heads can happen on one side of the coin, but there are two possible sides. 1 out of 2 is 50%. Another example is if we are drawing a card at random from a deck of cards. The probability of obtaining a heart from that deck of cards, there are 13 possible cards that are hearts in the deck out of 52 total cards. 13, the fraction 13 out of 52 simplifies to 1 in 4. So there's a 1 in 4 probability of drawing a heart. What is the probability of drawing an ace from a regular deck of cards? There are 4 aces in the deck out of 52 possible cards. 4 out of 52 simplifies to the fraction 1 out of 13. I'm going to say it again, that the idea of probability is identical to the concept of proportion. So, what proportion of cards in a deck are hearts? Well, it's still 13 out of 52, or 1 out of 4. And what proportion of cards in a deck are aces? It's still 1 out of 13. Proportions generally are expressed with decimal points, especially in this class. So the proportion of hearts would be 0.25. The proportion of aces, we're going to simplify to 0.08. So know that proportion and probability can be used interchangeably. Generally, proportion is going to refer to it when it's expressed in decimal points. Alright, so what is the role of probability in inferential statistics? Like I said, probability is used to predict what kind of samples are likely to be obtained from a population. Thus, the connection between samples and populations that we're going to use in this class is probability. Inferential statistics rely on this connection when they use sample data as the basis for making conclusions about populations. In other words, if we are interested in a population, let's say the population of all college students in America, we do not have accurate data about that entire population. It's impossible to test every single college student in the United States of America. Therefore, we take a sample of college students, we make it as representative as possible, but we know, because of the concept of sampling error, that there's going to be a difference between our sample statistics and our population parameters. But we can calculate with a certain likelihood or certain probability how close our sample is likely to match the population that it came from. And that's in part what we're going to be doing for the rest of the class. So you cannot predict exactly which values will be obtained for a sample. So that's an important point to clarify what I said before. You cannot predict exactly which values will be obtained for a sample, but you can determine what outcomes for a sample have a high versus a low probability. When a population of scores is represented by a frequency distribution, probabilities can be defined by proportions of that distribution. When we're using graphs, an easy way to do this is the proportion of area under the curve. Let's look at an example of what we're talking about here. So let's relate probability back to z-scores. So if we have a perfectly normal distribution which we often assume that when we're dealing with z-scores, we can use the area under the curve to find the probability of finding any type of outcome. For example, if you want to know how likely it is to find a score between 1 and 2 standard deviations above the mean, we can find this in a table or find this on a chart like this one, or a graphic like this one. The probability of us obtaining a value that is between 1 and 2 standard deviations above the mean is about 13.6%. So that's what we're talking about here. We'll go over some more examples of that too. So let's go over these examples right now. What is the area under the curve within 1 standard deviation of the mean? In other words, area under the curve, in this case, in this context, means the same thing as what is the probability of obtaining a score within 1 standard deviation of the mean. And I'll give you a second, pause the video and see if you can go through these 4 questions. Okay, I will assume that the video was paused for a minute. The area under the curve within 1 standard deviation of the mean is about 68%. Adding the 34.13 between the mean and -1 standard deviation, 34% between the mean and +1 standard deviation. What is the area under the curve between 1 and 3 standard deviations? That's about 16%. The area under the curve in the body below the mean, adding up those values, the area below the mean is about 50%, or is exactly 50%. Got to be careful about the wording there. Area above the mean also is exactly 50%. And what is the area under the curve in the tail above 2 standard deviations? Is about 3%. Actually, I gotta go back and correct that. It's about 2.2%. I'm doing my math wrong, or 2.3%. What about this question? What is the area under the curve above 1.6 standard deviations? It's a tricky question, because if you followed along with 1 through 4, you know that it's probably an easy way to do question number 5, but using the table or the graphic we have here, we can't do that. And the answer is that there is a table in the back of our book. It's table B1 is the label that it's given, in which we find other values besides just 0, 1, 2, and 3 for z-scores. 1.6 is included, as well as 1.43, 1.22. Any example with 2 decimal places you can find in the back of the book. We'll go through these examples in a minute. A note here, if we draw a vertical line anywhere in the normal distribution, that line can be represented by a z-score. The larger section that is carved out will be called the body of the distribution. The smaller section will be called the tail of a distribution. Let's go through an example of that. So if we draw, I wish I hadn't used graph paper because it just shows how bad my drawing skills are. Let's pretend that this is a normal distribution. If we draw a line here, this can be represented by a z-score. We have now divided this distribution into the body and the tail. The body and the tail. So we used the words body and tail before in this class. We're using them again in a different context to mean almost the same thing. Anytime we draw a z-score anywhere in the distribution, we can divide the distribution into a mean and a tail. So if we draw a z-score right here, the body of this distribution is going to be over here, and the tail is going to be the left side right here. So review those terms. We're using them in an almost identical way, but it's important to remind ourselves because of what we're dealing with in the table back here. So let's talk about the unit normal table. The unit normal table is going to give us several proportions corresponding to each z-score location, accurate to, I think, 2 decimal places is what this book uses. You can find tables that are accurate to more than 2 decimal places online. You can search for a unit normal table and find those pretty easily, but in this class, 2 decimal places is as accurate as we need to get. Rather than going through the information I have here listed on this slide, let's go straight to showing a small section of the unit normal table from the back of the book. So I recommend, if you've got your textbook handy, to flip to table B1 so you can follow along here. What I have on the slide is just a small slice of table B1. So you'll notice that table B1 gives us a list of z-scores. So column A is a list of z-scores, every possible z-score accurate to 2 decimal places. Column B gives us the proportion between, or the proportion in the body of the distribution at that z-score. The proportion in the body of the distribution at that z-score. So in other words, if we have a z-score of 0.33, let's say that this z-score in the top right hand corner corresponds to z equals 0.33. That means that the shaded region right here, the proportion in the body is equal to 0.6293. The unshaded region right here is the proportion in the tail, 0.3707. That's column C. And column D gives us one piece of additional information, and that is the proportion that falls between the mean and the particular z-score. So the proportion that falls between the mean and a z-score of 0.33 is equal to 0.1293. There are a couple more examples here on the homework and throughout the book. This is going to be important for the next few chapters, so make sure we get this down. Make sure you're able to read the table in the back of the book. Okay, so how do we use this table? To find the probability that is corresponding to a particular raw score. So X I usually use to stand for a raw score value. We need to, number 1, the table in the back of the book, table B1, the unit normal table, doesn't include raw scores. That wouldn't be very useful. It includes z-scores. Fortunately, we can convert raw scores into z-scores. So transform this raw score into a z-score. This is what we learned in the chapter previous. Step 2, with our new z-score, we look that up in the table B1. And then step 3, we can read across the row for that z-score to find the appropriate proportions and probabilities associated with that z-score. So to find the score, so notice this is the opposite. To find the raw score corresponding to a particular proportion, we would need to first find that proportion in the table in the back of the book, read across the row to find what z-score is associated with that proportion, and then transform that z-score into an x value. So we can go from a raw score to a proportion. We can also go backwards from a proportion to a z-score to a raw score. So another vocabulary term that we're going to need to know is the percentile rank. The percentile rank for a specific raw score value is the percentage of individuals with scores at or below that value. When a score is referred to by its rank, the score is called a percentile. The percentile. So here's how this relates to the table that we've been looking at. The percentile rank for a score in a normal distribution is the proportion to the left of that score, no matter where the score is in the distribution. So let's go through this example. If we have a z-score that is equal to positive 1, get your book out and look at your unit normal table. You can also find a unit normal table online and see if we can find the proportion of scores that are above positive 1, the proportion of scores that are below positive 1. Now, note that these two numbers should add to 1.00 exactly, with a little margin of error for cutting off decimal places. So take a minute to pause the video and do that. So I will suggest for most of the problems, actually, most of the problems we do for the rest of this class, it's very beneficial for me, and I suggest this to other people, to visualize the information you're trying to find using a distribution. So what I normally do for questions like this is, if I have a piece of scratch paper or I have my homework assignment, is to draw a little standard distribution, a normal distribution, and then mark approximately where 1.0 is. That way I can visualize what I'm trying to find. Once we've done that, we transform go through these 3 steps, transform our score into a z-score, which we already have the z-score, it's 1.0, look up the z-score in the table, and then find the proportion in the body, the proportion in the tail from the table. And these are the numbers that you should have come up with. So, applying that to the problem that we were originally looking at, what are the proportion of scores above a z-score of 1.0? That was the proportion in the tail. So about 0.16. And what proportion of scores were below a 1.0? That's 0.84. Now, if you started on the homework, or if you're looking through the chapter, you might have come to the realization that the unit normal table in our book does not give negative z-scores. The unit normal table does not give negative z-scores. So how do you deal with problems that require you to look up proportions for negative z-scores? And the answer is that, luckily, because the perfect normal distribution is perfectly symmetrical, the information that we find for positive z-scores can help us for negative z-scores. We just have to switch the numbers around. For a z-score of negative 1, we flip those numbers. The proportion in the body is 0.84, and the proportion in the tail is 0.16. Let's display that here. If I can find my cursor. Oh, it's yellow. Okay. Let's say we have a very lumpy, but we're going to pretend this is a perfectly symmetrical normal distribution. Z-score of +1 is going to be here, and a z-score of -1 is going to be down here. If I shade in the body for a z-score of positive 1. We looked it up in the back of the book. We know that what I just shaded in corresponds to a probability of 0.84. If I instead shade in the body of the distribution that corresponds to a z-score of -1, notice that although the location has changed, it flipped around a mirror image, we're also shading in 0.84, 84% of the area under the curve. This principle is important. Anytime we're dealing with negative z-scores, just know that they are the mirror image of their corresponding positive z-scores. Whoops. Okay. Remember we introduced the term a minute ago of percentile rank. Percentile rank is the scores that are equal to or below the z-score. In this case, with a z-score +1, that would be the proportion in the body, which is 0.84. Alright, let's do another example. What proportion of scores fall between z-scores of -1 and -1.5? Let's graph that, and then we'll wait. Alright. Let's do a normal distribution-ish. And the question is, what proportion falls between -1 and -1.5? Alright, so how do we find this information? Take a second to pause the video to see if you can do that based on the unit normal table found in the back of your book. Okay, now in the unit normal table in the back of the book we can puzzle out a few pieces of information. For example, what proportion of scores are below the value of -1? What proportion of scores are below the z-score value of -1.5? Using these two pieces of information, we can subtract them from each other to find just the proportion that is between -1 and -1.5. So let's look at that on the graph. So we found in the back of the book that the proportion in the tail for this equals -1. So this area right here was about 0.16. We also found this proportion here was about 0.07. But we're only interested in this small stretch right here, the proportion just between these 2 points. So, like I displayed on the slide, if we take 0.16 and subtract 0.07 from that, we come up with our value of 0.09. Now, this example right here seems pretty easy when it's laid out like this and we're going through it visually. So I want to emphasize that. I highly recommend to do these problems visually. Sketch out a little normal distribution. It makes things so much easier. Also, it's very important that we get this concept down. It's important for this chapter and upcoming chapters. Okay. We can also ask the question, what is a percentile rank for a z-score of negative 1.5? The proportion in the tail is a 0.07, approximately 0.07. Why are we looking for the proportion in the tail of a z-score of negative 1.5? Graph it out visually and notice that this is the opposite procedure for what we would use for positive z-scores. Okay. Let's look at this visually using some graphs. So if I ask the question, what proportion of scores are above a z-score of 1.50? Well, that's that answer we got a second ago, 0.0668. What proportion of scores are below? It's 0.9332. If we are asking about a negative number, negative 0.5. Now find these values in the unit normal table in order to follow along with this example. What proportion of scores are above a z-score of negative 0.5? That's about 0.69. And below is about 0.31. I'll suggest again, make sure you're following along and finding these appropriate numbers in the unit normal table. Okay, let's go through an example of something that we looked at a minute ago. What z-score corresponds to the 90 percentile mark of this distribution? So if you've paused and done the calculations, we should come up with a z-score of approximately 1.28. So next, what z-score captures the middle 60% of this distribution? In other words, what positive and negative cutoff point will leave 60% of the distribution in the middle? So pause and try to complete this question. Okay, this is a little trickier than some of the other questions that we have looked at, but the secret here is recognizing that if the middle 60% of the distribution is what we're trying to find, this leaves 40% of the distribution remaining, 20% at the top of the distribution, 20% at the bottom of the distribution. That 20% at the top and the bottom is what can easily allow us to look up the z-scores using those proportions. So if we're trying to find the middle 60%, that means that 40% is the remainder, 20% in each tail of the distribution. So what we can look up in the back of the book is a z-score that corresponds to having a tail whose probability is equal to 0.20. And we find that z-score is plus or minus 0.84. Let's go through one more example. What percentage of the distribution has an IQ above 130? Given the information above, what percentage of the distribution has an IQ above 130? Oops. So what we need to find here is we need to start by finding what a score of 130 corresponds to in terms of z-scores. We can convert the score of 130 using the equation from last chapter into a z-score of positive 2. We can look up a z-score of positive 2 in the unit normal table in the back of the book and find that in the tail of a z-score of positive 2 is about 2.3%. So 2.3% of this distribution has an IQ above 130. And I'm going to finish this off with a display of the normal distribution. This is something that we need to become moderately familiar with. Now, I'm not going to expect on tests and quizzes that students in this class have these numbers memorized, because in the real world, when we need to look up information about the unit normal table for actual experiments and statistics, when we're running statistics, we will have the unit normal table available. But it is important to remember that, for example, the relative size of the proportions in this table. Knowing that there is a larger proportion of the scores between 0 and 1 standard deviations than there is between 1 and 3 standard deviations, for example, is something that we will need to know. So the relative sizes of these cutoff points. That's where we're going to end for this lecture. Make sure to review the information on probability in the book, complete the homework assignment, and post if you have any questions. Thank you for listening.